Hello, I am Seema and welcome to part 14 of the chapter, The Solid State. In this video, I'm going to be solving a few in-text questions. These are in-text questions of your NCERT textbook. So I'll be first doing question 1.14, which reads that what is the two-dimensional coordination number of a molecule in square close-packed layer? When we say two-dimensional, the board is two-dimensional. We are talking of a flat surface. Or in other words, when we are talking of solids, we are talking of only one layer of the molecules. We're not talking of multiple layers, just one layer. And in a square close-packed layer, every molecule falls above the other one. Now, I've just arranged these here. You see, if each ball is a molecule, the other molecule falls exactly above the previous molecule and the next falls above it. Therefore, if you really look, these seem to be forming, if you see 4 of these, it forms a square. If you take 9 of these, it forms a square. So it is a square close packed. It's as closely as you can pack it. It's already been packed because you see the atoms are touching the neighbors, right? So this is and since it is only one layer of molecules, each ball being a molecule, it has only one layer of molecules. It is in 2 dimensions. That is why it is flat. You can see it. I can actually make the structure on the board if I drew these balls. So what is the two-dimensional coordination number of a molecule in square close-packed layer? What is coordination number? Coordination number is the number of neighbors that an atom or a molecule touches, right? Coordination number is not just the neighbors, but the neighbors that it touches. So if we look at this one of these balls, let us take the central ball here. How many neighbors does it have? If you see around it, what all do you see? You see all these atoms. There are 8 of them. Oops. I was not careful with my balancing. Okay. I'll have to rearrange these now. Okay. I'm going to play table tennis here. Okay. So if I'll have to be careful when I'm holding it now. So if I am So if you imagine this ball, I hope you can see it. I have to tilt it slightly, otherwise they fall. If I see this ball, how many neighbors does it have? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 balls that are around it. So it has 8 neighbors. So you would be tempted to say that the coordination number of any molecule or any ball, if you expand the two-dimensional structure, would be 8. The coordination number would be 8. But although it has 8 neighbors, it is not touching all of them. Take a look. This ball is touching this, it is touching this one, it is touching this one, and it is touching this one. Exactly, it is actually touching them. But if you look at these diagonals, the balls which are diagonally in the square, this ball, central ball, is not touching this, it is not touching this, it's not touching this, and it's not touching this. It's actually, although it has 8 nearest neighbors, it is actually touching only 4 of them. So, the coordination number of a molecule, what is the two-dimensional coordination number? Coordination number means the number of molecules that it is directly touching. So, the coordination number of a molecule in square close-packed layer would be 4. It will not be, you would be tempted to think it is 8, while it is not. It is actually touching only 1, 2, 3, and 4. So the coordination number is 4. So the answer for this question, what is the two-dimensional? You draw the molecule like this. If this is 1, this is the second one, this is the third one, this is the fourth one, and the 5th atom or the molecule. Now, it is touching these 4, and if you have these molecules here, as I showed you, the 4 molecules which are diagonally arranged, they are not touching this central ball. Do you see this? There is a gap. There's a gap here. I could color the gap to show you the gap there. Do you see? This is the colored area. It's not touching, not touching, not touching this, and not touching this. But it is directly touching this one, this one, this one, and this one. Therefore, what is the coordination number? What's the answer for this? Answer of this question would be the coordination number. The coordination number is 4 in 2 dimensions. So now we come to the next question. The next question is, a compound forms HCP structure, hexagonal close packed structure. What is the total number of voids? If you talk of hexagonal close packed structure, just shake it a little and automatically it will acquire the hexagonal structure, because that is actually the most efficient structure. So do you see, every ball falls in the groove of the ones 2 balls before it. It falls in the groove. So this packing is more efficient because it is here. I should reduce one ball here, then it will actually, yeah. So every ball actually falls into the groove of the lower 2. Yeah. So since it falls into the groove of the lower 2, now this central one has 6 atoms around it. In 2 dimensions, it's close packed. It will actually be touching 6 neighbors. So the coordination number is 6, and therefore the packing is more compact. If you see here, it is touching all 6 in 2 dimensions. But we are not talking of a 2-dimensional lattice in this question. We are talking of the 3-dimensional lattice. If you go back a few videos, I have actually shown you the different types of voids that are made by arranging different layers of these atoms or molecules, the particles that compose the solid, to give us different types of voids, that is tetrahedral voids and octahedral voids. So this question involves that. So if you do not understand, as I explained, I would encourage you to watch those videos first so that you understand this question. Let me now read the question. A compound forms a hexagonal close packed structure. What is the total number of voids in 0.5 mole of it? How many of these are tetrahedral voids? Now, we know that 1 mole of any substance means how many particles? 1 mole of molecules or 1 mole of atoms or composing particles is equal to the Avogadro's number Na, which is 6.022 into 10 to the power 23 molecules, atoms, ions, whatever the particle is. So a compound forms an HCP structure. What is the total number of voids in 0.5 mole? 1 mole would be this. Then what would 0.5 mole of the substance, how many particles would it have? If 1 mole of substance has these many particles, 0.5 mole will have 0.5 of this, which means it is half of this. 0.5 into 6.022 into 10 to the power 23, which will be half of this, which is 3.011 into 10 to the power 23 particles. Okay, the particles could be atoms, they could be molecules, they could be ions. So it says a compound forms an HCP structure. What is the total number of voids? Now he's not talking of the number of particles, he's talking of the number of voids. What is the total number of voids that are there in 0.5 mole? So in 0.5 mole, we know that these are the number of particles. Why did we want to find out the number of particles? Because we know that for a substance in HCP packing, the number of tetrahedral voids is equal to, let us say that this number is n, any number n. tetrahedral voids would be twice of n. Okay, they'll be twice the amount of atoms or composing particles. Tetrahedral voids are twice the number. What is the number n here? It is 3.011 for 0.5 mole. The number of particles is 3.011 into 10 to the power 23. So how many tetrahedral voids would be there? They would be twice of this number, which is equal to 2 into 3.011 into 10 to the power 23, which would come out to be equal to again 6.022 into 10 to the power 23. So there will be how many tetrahedral voids? They would be 6.022 into 10 to the power 23 tetrahedral voids. And what is the number of octahedral voids in a solid? The number of octahedral voids is equal to the number of particles, composing particles. The number of composing particles are how much? 3.011 into 10 to the power 23. So octahedral voids are 3.011 into 10 to the power 23, while tetrahedral voids are twice of this, that is 6.022 into 10 to the power 23. So the question says, what is the total number of voids? So what will be the total number of voids? Total number of voids will be is equal to total tetrahedral in plus octahedral. Okay, octahedral voids. The tetrahedral voids are how much? They are 6.022 into 10 to the power 23 are tetrahedral voids, and octahedral voids are 3.011 into 10 to the power 23. So the 10 to the power 23 is common. 6.022 plus 3.011 would make it 9.033 into 10 to the power 23 is the total number of voids. Out of which, how many are tetrahedral? 6.022 into 10 to the power 23 are tetrahedral voids. Right, so this was question 1.15. So give me a moment, let me write the next question. Alright, so now this is question 1.16. The question reads, a compound is formed by two elements M and N. The element N forms CCP lattice and atoms of M occupy 1/3 of the tetrahedral voids. What is the formula of the compound? By knowing the ratio, the minimum ratio between M and N, you can calculate the empirical formula, which could be the molecular formula too. So we'll assume that that formula that we get would be the molecular formula or the empirical formula of the compound. So a compound is formed by two elements, M and N. What are the two elements? M and N. The element N forms the CCP lattice. N forms the CCP lattice. In CCP lattice, whatever is the number of atoms, the number of tetrahedral voids is twice of that. And the number of octahedral voids is equal to the number of atoms. So whatever is the number of atoms of N, since N is forming the entire lattice and M is only occupying the voids. So the element N forms CCP lattice and atoms of M occupy 1/3 of the tetrahedral voids. If N, let us say, if N, number of atoms of N is equal to 1, then number of tetrahedral voids, how much would they be? They are twice the value of N. Since N is 1, that will be equal to the number of tetrahedral voids would be 2. Now let us take the ratio of the two. This is M is to N. If N is 1, then what is M? M is 2, M is 1/3 of the tetrahedral voids. What is the number of tetrahedral voids? 2. Right? So it is 1/3 of the tetrahedral voids. Since the number of n is 1, the number of tetrahedral voids would be 2, would be twice of this. So m would be 2/3 of whatever is the number of atoms of n. Since we assumed that to be 1, we have this as 1. You could have written it as if it was n also. You could have written that if n is, the number of atoms of n is n, then this would be, the number of tetrahedral voids would be twice n, and it would be 1/3 of twice n, and the n and n would get cancelled. That's why we kept it as 1, because that value, the value of n, whatever it is, would anyhow be cancelled. So it is 1/3 of this. So in other words, it is m is 2/3 is to n is 1. If I multiply both sides by 3, let us multiply both sides by 3, the 3 gets cancelled, the value of m is 2 and value of n is now 3. So that is the ratio. For if there is m, there would be 2 m's and n would be 3. So m2, n3 would be the formula of the compound. For 2 m's, there are 3 n's. So m2, n3 is the formula of the compound. Now, let us come to the next question. The question is question 1.17, which says that which of the following lattices has the highest packing efficiency? In previous videos, we have already calculated the packing efficiency for different types of unit cells or lattices. Simple cubic lattice, body-centered cubic, and HCP lattice. For simple cubic, how much is it? It is 52.4%. The 52.4% is the efficiency, packing efficiency. BCC is 68%, and HCP is 74%. So which of the following lattices has the highest packing efficiency? Whichever has the highest percentage of atoms per unit volume, that is the highest packing efficiency, which comes in HCP, which is 74%. So HCP or hexagonal close packed lattice, hexagonal close packed lattice has the highest packing efficiency of 74%. So that's your answer, right? Now give me a moment to write down one more question before I wind up this video. All right, so now this is the last question that I'll be doing in this video. This is question 1.18. It says an element with molar mass 2.7 into 10 to the power minus 2 kg per mole. Molar mass is capital M, right? Capital M is 2.7 into 10 to the power minus 2 kg per mole. Answer or solution, okay? Forms a cubic unit cell. It forms a cubic unit cell with edge length of 405 picometer. So edge length would be A. A is equal to 405 picometers. Do you see here kg? So we would be converting this into meters. So this 405 picometers would be equal to 405 into 10 to the power minus 12 meters. So if you convert it into scientific notation, you would put the decimal after 4. So it will become, you'll take 2 zeros from there. So 4.05 into 10 to the power minus 10 meters. Do you get me how I did this? It was 405 into 10 to the power minus 12 meters. So when I try to convert it into scientific notation, I put the decimal here. So if I put the decimal here, I have to multiply it by 100. So I remove 2 tens, 2 zeros from here. So I get 4.05 into 10 to the power minus 10 meters as my the side, the length, edge length, sorry. So if its density is D, Density is 2.7 into 10 to the power 3 kg per meter cube. Right? What is the nature of the cubic unit cell? We know that density is equal to D is equal to Zm over A cube Na. Remember? So let us, in this we know D, we know what is the value of Na. It's a constant, we already know it. Na is 6.022 into 10 to the power 23 atoms per mole. Okay, so that is the value of Na. And we are given D, we are given M, we know A, so we can find A cube, and we are supposed to find out the value of Z, because the value of Z will give us an idea of the kind of unit cell it is, cubic unit cell. If the value of Z is 1, then it is a simple cube. If the value of Z is 2, then it is a body-centered cubic unit cell. And if it is 4, then it is a CCP or an HCP. So let us just substitute all the values and calculate the value of Z. So now if D is equal to Zm A cube and over A cube Na, then Z would be equal to D into A cube into Na upon N. We are just cross multiplying so that we get the value of Z. Now substitute all the values. Z would be equal to, what is the value of D? Is 2.7 into 10 to the power 3 kg meter minus 3. Okay? Into, what is the value of A? A is 4.05 into 10 to the power minus 10 meter whole cube. Right? Then into Na is 6.022 into 10 to the power 23 atoms per mole. Right? And what is the molar mass? Molar mass is 2.7 into 10 to the power minus 2 kg per mole. Right? Now 2.7 and 2.7 get cancelled. The marker needs a change again. Since I'm taking fewer classes, the markers hardly work now. So 10 to the power 3 here, you have 10 to the power 3 and 10 to the power minus 2. Alright, 10 to the power 3, here you have 10 to the power minus 30. This meter, if you bring it out, it becomes meter cube. So meter cube and meter minus 3 will get cancelled. Do you see? The units will get cancelled. We always have to find out Z is only a number, so it should not have units. So if you cancel out the units first, you know whether you've plugged the quantities correctly or not. So kg and kg will get cancelled here. Per mole here and per mole gets cancelled here. Atoms is nothing but a number. So now we have no units. So the value of Z is atoms per, in other words, atoms is the number of atoms in one unit cell. So we have plugged the values correctly. As far as the powers of 10 are concerned, 10 to the power 3, 10 to the power minus 30, 10 to the power 3 into 10 to the power minus 30 into 10 to the power 23, right? And 10 to the power minus 2 would become how much? 10 to the power minus 2, if you bring it up, would be 10 to the power 2 again, right? If you bring it up, it becomes 10 to the power 2. So 10 to the power 3, 5, 23 plus 5 is 28. So 10 to the power, this would become, the positives are 10 to the power 28 and the negatives are 10 to the power minus 30. So 10 to the power minus 3 will remain. And when you solve all of this value, that is 4.05 into 4.05 into 4.05 into 6.022, and then you manage the tens also. If you calculate it, I have done it using a calculator because I really do not, the tens have to be, I have to be bothered about, but the rest, if you solve this, it will come to be 4.004. Z would be equal to, which is approximately, Z is approximately equal to 4. Sorry, 4. So if the value of Z is 4, then what is the, what kind of unit cell is it? If the value of Z is 4, then it is either a cubic CCP or an hexagonal close packed, or HCP. It is a CCP or HCP, or you would say FCC lattice. HCP is hexagonal close packed. So it's not cubic. So you would say it is either CCP or it is face centered cubic. FCC, right? So it is either CCP or if it is an FCC, face centered cubic unit cell. So these were the in-text questions. Before we move on to the next topic, that is imperfections in solids. With this, I'll wind up this video. If you wish to watch other videos of this chapter, please click the link that appears on top of this video. And if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.